Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 2, A History of the Atom. Episode 4, The Corpuscular Atom. In this episode, we emerge from the Great Mortality. Well, sort of. As I mentioned last time, while the initial appearance of the bubonic plague was certainly the most generally devastating of the waves of it, subsequent outbreaks of the disease would continue to roll across Europe and England for another 3 centuries, causing death, misery, and general upheaval. I'll leave it to the real historians to discuss the long-lasting impacts of this ongoing disruption to the fabric of Europe, but I don't think there can be much doubt that it's a watershed event in Western history. For our story, the plague's undermining of the various social structures, along with the development of several new technologies, sets the stage for the brewing forces of the Italian Renaissance to boil over and spread throughout Europe. The development of the printing press, the use of gunpowder, and the widespread adoption of the compass for use in seafaring lead to fundamental changes in almost every aspect of European life. However, it's not just the social or political aspects that begin to change. Additionally, there is a willingness to challenge the accepted ideas and philosophical frameworks that were in place, most notably Thomas Aquinas' synthesis of Aristotle's philosophy and Christian theology. More broadly, there is a reconsideration of the scholastic emphasis on rationalism in favor of empiricism, beginning with Robert Grosseteste, Roger Bacon, and William Ockham prior to the plague. All of this leads to a post-plague intellectual environment that is ripe for the consideration of new ideas or reconsideration of old ideas in a new light. Now, there are 2 things that are important for us to keep in mind as we move forward. The first is that academic or scholarly communication was not what we would think of today as a very fast-moving process. Nowadays, we're used to lightning fast, almost instantaneous transmission of knowledge. Even in the relatively slow world of academic publishing, the time from submission of completed research to widespread publication is usually only about a year. Compared to the time it took for scholars to communicate in the 15th and 16th centuries, this would have been an astoundingly quick turnaround. Back then, when academic publications and journals were non-existent, most publication was done through personal letters or occasional hand-copied manuscripts. This meant that the spread of new ideas was slow, uneven, and impeded by the nearly constant warfare European powers seemed to engage in. After the development of the printing press, the publication of new ideas happened at a greater pace and to a wider audience, but getting one's ideas out still took a lot of time and was pretty expensive. The second thing to understand is that the nature of matter wasn't really the big intellectual puzzle everybody's trying to solve at that point. The bigger issues on the agenda, as it were things like trying to figure out how to fix the Julian calendar, which was about 2 weeks out of whack by this point, and figuring out the answer to the much deeper and more controversial question of what was the Earth's place in the universe. I'll have a series on both timekeeping and what's generally known as the scientific revolution in the future, so I won't say much here other than to point out that nearly every individual I'll discuss in this episode will be spending most of their time and energy working on those problems, with only a fraction of their intellectual output being devoted to the idea of atomism. One final reminder as we set out into new waters. Chemistry, as we think of it nowadays, doesn't exist yet. We're still living in the time of alchemy in Europe, and alchemy was a pretty touchy subject. While still widely practiced at the time, it was variously discouraged, regulated, or outright banned by both the political and religious authorities of various regions. The period after the plague through the 1600s is a startlingly violent and intolerant time in Europe, and those who were thought to participate in things not very well approved by those people and organizations who were in power often met with pretty harsh resistance. Thousands of women were rounded up and executed as witches for little more than practicing what we might think of as medicinal chemistry nowadays. And those attempting to investigate transmutation often had to do their work in secret and communicate by code in their writings. This would slow the progress and communication of the work tremendously and would also help foster ambiguity and charlatanism throughout the intellectual community. So, where does this leave us? As I mentioned last time, in 1417, a manuscript was discovered in a German monastery that was a copy of Lucretius's epic poem wherein he explained the ideas of Epicurus, originally for his Latin readers in ancient Rome. This, along with what was known from the translated writings of Aristotle and the new support of atomism from scholastic thinkers Occam and Thomas of Autrecourt, revived the idea of atomism for a whole new generation of scholars. Due to the slow-moving nature of scientific communication, however, it takes a while before these ideas begin to show up in broadly communicated works. Our story, therefore, picks up in the early 17th century with two pairs of writers. First, Giordano Bruno and Galileo Galilei, and second, Pierre Gassendi and René Descartes. Bruno and Gassendi were both priests in the Catholic Church, while Galileo served as a sort of administrator for the church for a good bit of time. So let's look at each in turn. The first person we wish to consider is the tragic figure of Giordano Bruno. Born in 1548, just 5 years after the death of Copernicus and that scholar's publication of the heliocentric model of the solar system, Bruno would grow to become a radical thinker in a time when dissent was often met with violent opposition. Like a number of figures of his time, he would adopt several controversial ideas, including a belief in the correctness of Copernicus's model, a rejection of Aristotle's belief that the earth and the heavens were made of different things, and most importantly for our story, much of the philosophy of Epicurus and atomism. While he agreed with the idea of an infinite number of atoms, and indeed an infinite number of worlds in a universe populated with any number of inhabitants, he rejected the idea of these atoms acting in a purely mechanistic fashion. Rather, he seemed to believe in a sort of pantheism where each atom emanated from God and carried within it a connection back to God in such a way that it would do explicitly his will. Bruno published his ideas where he could, and unfortunately for him, many of his writings challenged a lot of the central tenets of the Christian faith, including, probably most importantly, the doctrine of transubstantiation. While many a writer has suggested, often strongly, that he was persecuted mainly for his scientific views, it is likely more accurate to say that this portion of the charges leveled against him were only a small part of a larger case of heresy. Over time, he was convicted multiple times of spreading false truths and subjected to increasingly stiff penalties until he was finally burned alive on the Campo di Fiore in Rome in 1600. Bruno's better known and scientifically more successful contemporary was one Galileo Galilei. He was, almost without question, the finest natural philosopher of his age, and a pretty good mathematician to boot. His scientific contributions were numerous, but his name is now most commonly associated with his work in astronomy and the debate over Copernican cosmology. Like Bruno, he rejected the Aristotelian idea that there were separate elements for the heavens and the earth. His telescopic observations of the Moon, Jupiter, and Saturn in 1609 and 1610 established that the heavens could be and likely were made of the same stuff as everything else. Well, at least for those not dogmatically welded to the natural philosophy of Aristotle. Additionally, he wrote extensively showing that the physics of Aristotle was almost certainly in error. What should be noted is that much of his work in the field of physics assumed that phenomena were a result of matter being in motion. In this, Galileo professes himself to be a staunch supporter of the ideas of Democritus and Epicurus. It is here that he rejects some of the most fundamental tenets of Aristotle, which becomes the root of the conflict with the church hierarchy that he'll encounter. I'll be recording a supplemental episode about the life of Galileo when we reach the series on the scientific revolution, and so I don't want to spend much time here discussing the ongoing debate Galileo engaged in. But it should be stated that much of Galileo's work struck at the foundational doctrines held by the Roman Catholic Church at a time when the Church was politically vulnerable and not much receptive to dissent on any front. Like Bruno, Galileo faced a certain number of sanctions for his ideas. The Tuscan natural philosopher, however, was more pragmatic and willing to moderate or repudiate his views in order to avoid harsher and more permanent penalties. A third contemporary here that we should mention in passing is Francis Bacon. While Bacon is better known for establishing a process by which science could be better done, he was also, at least for a time, an atomist, following in the footsteps of earlier British philosophers like Henry Percy. Later in life, Bacon pulled back from atomism as he found little empirical evidence to support it, but his writings kept the idea in the forefront of intellectual circles and was influential for the next generation of thinkers in England, most notably Robert Boyle and Isaac Newton. This leads us to the two figures who will engage the idea of the atom in fundamentally oppositional ways, Gassendi and Descartes. Pierre de Gassendi was born in 1592 in the Provence region of France. Educated as a priest, he took holy orders in 1617 after studying philosophy and receiving a doctor of theology. In that same year, he took the chair of philosophy at the university in Aix-en-Provence, beginning what would be a long academic career that included a number of position changes. He lectured primarily on Aristotelian philosophy and engaged in conversations and debates with the contemporary figures of his time, including Kepler, Galileo, and of course, as we'll mention, Descartes. He made a number of scientific contributions, including making the first observation of the transit of Mercury across the face of the Sun, based on the predictions made by Kepler. Gassendi was such an accomplished writer that historian Edward Gibbon would say that he was, quote, the greatest philosopher among literary men and the greatest literary man among philosophers. Gassendi's overriding goal in his philosophical work was to attempt to reconcile the new ideas emerging in European humanistic thought with his Christian faith. In this, he would become, like so many of his contemporaries, dissatisfied with the ideas of Aristotle and would press for a more empirical approach based on gathering information solely using the senses. From here, he would advance a version of atomism that began with the ideas of Epicurus, but that removed the purely mechanistic requirements so that God could have a role. In this, he rejected the Epicurean idea that atoms were both infinite in number and duration, and said that God had created them. He also claimed that the soul was not made from atoms, thus removing the requirement that it, the soul, would be temporary. Still, he kept the Epicurean ideas of void, constant motion, and combination. To this, he added a first good attempt at the idea of a molecular theory that attempted to explain how various substances arose from combinations. Now, Gassendi's ideas must be contrasted with those of his contemporary René Descartes. Descartes is known as a brilliant mathematician who unified the fields of geometry and algebra into what we call now analytic geometry. He's also thought of as the founder of modern dualistic philosophy, and it's in this later role that we'll consider him for the time being. Descartes is usually lumped in with the anti-atomists in the fact that he rejects both the idea of the void and that atoms are what make up the essence of all objects. As a mathematician, Descartes was primarily a rationalist in his metaphysics, believing that the mind alone could understand the nature of reality. For him, matter and space is inherently the same thing, and so to define matter as atoms moving through space made no rational sense. Additionally, he claimed a completely separate realm of being for thought, soul, and God, that while not material, was every bit as real as those things that are. This dualism is at the foundation of all of his philosophical work, including his metaphysics. In light of these two things, Bernard Pullman excludes Descartes from the list of atomists because of his rejection of those ideas. The debate between Descartes and Gassendi defines much of the scholarly conversation about atoms during their time. What is important to note, however, is that both men are moving away from a purely Epicurean atom which was indivisible. In this, we see the rise of what is known as corpuscularism. In this, while there is an atom, it is said that it may be possible to divide that atom or at least penetrate it in some way. In other words, atoms lose the property of indivisibility. It was no longer thought to be some infinitely hard object. Gassendi needs this property in order to explain combination, i.e., build molecules, while Descartes will put forward the idea that matter is made up of swirling vortices that leave no space between them and hence no void, but that can sort of be squished if need be. Now, lest you think that the only thing going on in European science during this time were a bunch of philosophical ruminations about the nature of matter, we should spend some time talking about the line of experimental work that will become very important during this period. Around this time, the practice of alchemy began to change as the need to create gold from baser materials was undermined by the flood of gold arriving from the New World. Also, the number of alchemical charlatans began to outnumber those attempting to do honest work, and so something began to shift. Alchemical research began to change its focus towards medicinal chemistry and understanding the nature of the substances being worked with. This thread of our story begins with Jan Baptista von Helmont, a physician and philosopher who lived from 1580 until 1644, making him a contemporary of Galileo. Helmont studied a number of topics and lived both in the more archaic world of mystical alchemy and the emerging realm of empirical investigation first put forward in the field of chemistry by German physician and philosopher Paracelsus. Helmont worked on a number of projects, but is best known for two. The first was his attempt to track the mass of a changing system to determine if it was increased during a process or not. While his willow tree experiment was rife with errors, it was the first good attempt to establish whether matter could be created or destroyed, something he rejected. His second piece of work was his description of a whole new class of substances, gases, which he showed to be different than the air all around us. The name was likely taken from the Greek word chaos, and the subject was a difficult one to study at first. Helmont likely worked with mostly carbon dioxide gas, though he would produce nitrogen oxides, such as what we now call laughing gas, chlorine gas, and mixtures of nitrogen, methane, and other substances. The difficulty was that Helmont didn't realize that a gas would take up significantly more volume than other forms of matter, and so he kept bursting his fragile glassware, which led him to suspect that gases couldn't be contained. It would fall to the Benedictine monk Dom Perignon to show that it could be done with the champagne he was able to produce in glass bottles sealed with cork. Following this, Jean Bernoulli would use a magnifying glass to ignite gunpowder in a flask. By running tubing from the flask to a vat of water, Bernoulli was able to avoid the exploding glassware problem Helmont had, and he was able to show that gases occupied a much greater volume than solids do. All of these developments lead us to our next figure, Robert Boyle. Boyle, who was the son of a wealthy Irishman, lived from he lived from 1627 right up until 1691, which made him a contemporary of both Robert Hooke and Isaac Newton, along with Gassendi and Descartes. Working at Oxford, Boyle was part of a group at the university known as the Invisible College. It is here that he began his scientific researches on a wide array of alchemical and physical systems. Working with Robert Hooke and an air pump Hooke had developed from the work of Otto von Guericke, Boyle began creating vacuums in order to understand what happened to gases in evacuated chambers. It was through this research that Boyle established the physical law that bears his name, that says that the volume of a gas varies inversely with its pressure. In other words, Boyle's law says that if you make a container holding a gas larger, the pressure that the gas exerts on the walls of the container will decrease. He also performed a large number of other experiments in order to collect more information about the behavior of alchemical systems. While much of this work was truly brilliant, as an example, he was the first to establish that sound could not travel through a vacuum, his greatest contribution was to put into explicit practice the methods of scientific inquiry developed by Francis Bacon, and he did so in meticulous detail. His unflagging attention to the clear, quantitative work is shown in his book, The Skeptical Chemist, which was published in 1661. Following the model of Galileo's dialogue, The Skeptical Chemist is written as a conversation between four friends with the purpose of showing the inherent flaws in the systems of Aristotle and Paracelsus. In the book, Boyle undermines the Aristotelian idea of an element as something that must be present in all substances. He argued that there might well be more than 4 or 5 elements, and there could be substances that lacked more than one of these. His views on atomism were broadly similar to those of Gassendi, from whom he likely acquired them. While also an advocate of corpuscularism, Boyle was of the opinion that atoms did not divide during regular chemical or physical processes. Additionally, he felt that it was the shape of an atom that determined its physical and chemical properties. In his work, Boyle begins the development of a rudimentary kinetic theory of gases that relies on the idea that these gases would be made of atoms. This is something that we'll return to in the work of later scientists. The final figure we'll consider in this episode is Roger Boscovich. Born in the Republic of Ragusa in what is now Croatia in 1711, Boscovich was educated by the Jesuit order and spent most of his life in Italy. He was a polymath who worked in a wide array of topics in physics, astronomy, mathematics, and philosophy. His contributions in science are too numerous to mention here, and so we'll focus on his mathematical work towards establishing a framework of a particular type of corpuscular atom. To understand Boscovich's work in context, however, we have to go back just a bit to a debate between two of the greatest minds in the Western intellectual tradition, Isaac Newton and Gottfried Leibniz. While both men make significant contributions in many areas and vie for primacy in developing the mathematical field of calculus, we will focus here on their views on how actions occurred in the material world. Newton was an atomist who believed in corpuscles and void, going so far as using them in his explanations of the propagation of light. To this picture, he added 2 very important components. The first was that atoms now had a property known as inertia, which was the tendency for an object to continue in motion or to be at rest. The second was the development of a universal law of gravitation. Gravity was a force that could act at a distance to attract particles to each other. This force, first demonstrated on the scale of the celestial, was said to act on all bodies with inertia, and thus it affected the motions of atoms. This force both eliminated the need for the Epicurean swerve, which we discussed a few episodes back, that was needed to generate interactions in Epicurus's model, and it was able to define a quote-unquote down as a preferred direction in certain cases and in certain types of motion. This atomic worldview was known as being mechanistic in that it relied on mechanical interactions between atoms to produce motion and force. Gottfried Leibniz, on the other hand, offered a fundamentally different approach to the problem of motion. Leibniz believed that there were an infinite number of monads, non-material and infinitely small. Those familiar with the differential element in calculus will not be surprised that Leibniz espoused such an idea. Leibniz believed that what caused motion were dynamical forces emanating from these points of energy. As such, while one might think of these things as being atomic, they are only so in a strictly metaphysical sense. Leibniz rejected the idea of an indivisible object that would have spatial extent as proposed by Epicurus, as well as the idea that monads would directly interact with each other. So with that brief introduction to the dominant ideas of the time, we arrive at Boscovich. Now, Boscovich was kind of a student of Newton's ideas, but his model was an attempt to reconcile the two competing hypotheses of Newton and Leibniz into one single description. His model has been called by a guy named Bachelard the punctual atoms. And what Boscovich had in mind was an object that had no spatial extent, much like Leibniz's monad, but that was a center of force that created interactions with other atoms in the vein of Newton. These forces would be attractive at longer distances, thus giving rise to gravitation, but repulsive at very short distances, thereby creating a sort of fuzzy indivisibility favored by the corpuscular atomists. What is interesting to note is that this is the same type of idea that can be found in the atomic hypotheses of both the Hindu philosophers of ancient India and the Arab atomists of the Middle Ages. Boscovich's atom was very attractive to a number of the philosophers of his day, most notably Kant, who preferred the mostly dynamical approach of Descartes and Leibniz to the mechanistic one provided by the English empiricists Boyle and Newton. This schism, by the way, between the approaches of rationalism and empiricism in considering the nature of matter is just one instance of a broader scientific debate that had begun back with Plato and Aristotle and that continued into the 20th century. As we close this episode, we are finally at the point where enough chemical work can be done in order to accumulate data that will begin to answer our age-old question of whether or not there are atoms, and that's where we're going to begin our next episode. Now, I should mention that due to traveling over the next week or so, it's unlikely that I'll be able to get the next episode out on the usual Sunday publication schedule. If all goes well, I should be able to do my research and writing on the road, and I expect that I'll be able to release the chemical atom into the feed on Monday, so be looking for it then. As always, thanks for taking the time to listen to the podcast. If you'd like to keep up with some various science news developments each day, I would invite you to like the podcast Facebook page, which you can find by searching the podcast title there on Facebook. Also, feel free to leave comments or reviews on any of the places you happen to find this podcast. So until next time, full sails on your journey.